So in the last tutorial we talked about the TX unit. So this is what it looks like. Out of the whole outputs we choose only 2 because that's what we'll be needing for the top level, and this are the inputs. So let's go over to RS unit. This is what the top looks like. So let's go over inside the circuit and see how it works. So here in the RS unit there is so much data delay. So the first clock cycle receives the RS data here, then takes it to the RS data delay 1, delay 2, delay 3 before the RS data delay itself. So all these are used to set the data to know that if this is a actual data being sent or maybe an error or something. So this is where we confirm this. So it checks if all of them is 111, that means there's still a issue, or likewise set it high if it's in 1, else set it to 0. So this is how we check. Remember I told you that a 0 indicates a start bit. So once you receive a 0, the start bit starts. Then you have your RS clock here, which comes in here, and then we did just something similar how we get the clock edge, RS clock edge. So when you go through the code, you see a lot of places where we got the clock edge. So this is how we did to get them. You take the actual signal and you take the signal after a clock pulse where you knot it, and then you'll be able to get the clock edge. So just like I told you, the only difference between the actual signal and the clock edge is that the clock edge is more precise actually. So you can as well use the actual signal there. Then you have your RS start bit. So once you have a data edge, you can set a start bit. Then you have your RS clock count. So this baud format and the word format also, is used at the receiver. So the transmitter and the receiver, we have to set them. We have to set this baud format and word format. So you know in UART it has configurations, so there should be a determined mode of transmission between the transmitter and the receiver in terms of how are the bits arranged. So whatever is the baud format on the transmitter should be the same thing on the receiving end. So just the way as I showed you, so that's the same thing that is happening here. So here will be bit 3 divided by 16 and this bit 5 divided by 64 coming from the RS clock count. Remember in the last tutorial we did it using the TS clock count. So what is the job of the baud format? It helps us to choose what format are we using. Are we using the original RS clock? Are we using a divided by 16, or are we using a divided by 64? So at the end we get the RS baud edge. So then our receiver tracks 3 different types of error. It checks for a frame error, it checks for an overrun error, and it checks for a parity error. So here the errors: framing error, this framing error, the overrun error, and the parity error. So to check the framing error, so this particular signal here is the RS state. Let me go down so you see it. So it's coming from here, the RX state. So at state 9 is assumed to be the last state of the receiver. So when it's at state 9, it does a lot of final calculations, that is including this error checking. So first of all checks if it's at state 9, then yes, then it comes here and checks for this framing error. So how does it check? It checks one, this bit here is your receiver, the RS data, your receiving data. So it comes and it will check if your received data is equal to 1. This should be 0, else the framing error will be 1. So when it's bit 9, the RS data should be the stop bit, and the stop bit is always 1. So if by chance when it got to 9 and it checked and it didn't receive a stop bit, it's going to output 1. That is when the received data is 0, it's going to indicate a framing error. So then the overrun error also, same thing, it calculates as when it is in bit 9. Remember, these are the receive baud edge. Let me highlight it so you see this. This multiplexer went through all the outputs here. All the outputs. This highlighted multiplexer is for synchronizing. It comes from the receive baud edge. See where it came from the receive baud edge. So that's what all those first multiplexer does. So then it checks for the overrun error and the parity error. The parity error we use from the parity bit generator to check. It checks at bit 8. The overrun error checks at bit 9. Then word format and your RX state. So I won't really go deep explaining this. On the code itself, this is RX unit. When you come down, you see how all the states are affected. This is it. I reset, all the errors are 0, registers are 0, parity bit RX value 0, 0. The RX state starts from 1, 1, 1. So first, after it checks, is another state. So this is a state machine here. Checks when is 0, 0, 0, when is 0, 1, 1. So it checks when is 1000. Checks again when is 1001. So that is majorly what this RS bit does. The RX state, sorry. So it determines the state of the reception of data. So this is the top unit of the RX unit. These are the inputs. These are the only selected outputs. Now, in the miniuart top, we've included them here. This, the top part, we included the RS unit and the TS unit as a sub-circuit for the top part of the miniuart. So this serves as the part where the receiver and the transmitter, where the receiver and the transmitter were combined together to make up the full UART circuit. So there's really nothing much happening. So this DCD, I'll make it a separate tutorial when I'll be doing the testing. Is used to diagnose data. This whole place, it wasn't really used for the UART transmission aspect. Then again, sorry. The reset, the CS, the chip selects the miniuart sub-circuit. The read not write, where if it's on is reading, if it's off is writing. So you have the address, means you are selecting here also. Then you have the data in, the data that is coming out from the CPU. Then you have your data out, the data that is going to the CPU. I just want to rush the video, so I will explain this. I talked about the status register in the tutorial. I showed you what each bits were. Like take for example the 0, you saw where it came from. It's coming from the DRAD bit here. Then bit 1 is coming from this CTS scan something. Bit 2, I highlighted it, let me see, it's coming from the DCD. So bit 3, bit 4 and the rest. So that is how they make up this status register. So aside from that also, we have the control register. Then these are the top part of the sub-circuit. These are the only choosing inputs, and these are the only needed outputs from the UART. So let me just simulate this quickly. So assuming I'm trying to, okay, before that let me make some settings first. We'll be using a clock. Sorry. Clock is here. Okay, sorry. So this is, let me get a clock for it. I'll connect it to the main system clock here. Disconnect it. Then let me connect the RSC, the TSC, because they'll be using the same clock, just like I explained, the board clock. So now let me start this transmission. So first of all, I select the chip select, means I'm selecting the miniuart. Then the read write needs to be off to know that I'm actually writing to the UART sub-circuit, not reading from it. Then I need to turn on the, okay, let me set the data to something like this. So what I'm trying to do here is I'm going to send this data through the transmitter and receive it back through the receiver. So if it's coming out through this transmitter, then I'm going to take it to the receiver here. I don't know if you understand what I just did. This data here is for the transmitter, the data in for the transmitter. Then once you send it in here, I already explained how the transmitter works and generates this transmit bit. So I'm now taking this transmit bit back to the receive bit of our receiver. I know I've disconnected this actual receive bit and connected this receive bit. So when it's done receiving, the output is going to show here. So that is just what I'm trying to achieve here, to show how this UART works. So let me start. So first of all, let me reset it. Turn it off. So then, sorry, was doing some error checks. So now let's test it. Just the setting. Once it's coming out of the transmit, it's going into our receive bit, and let's know if you're going to get the same after the transmission at our receive bit. Get this data into this data out. So let's go. So first of all, do the reset. And after the reset, the transmit bit is steady high. It's pulled high until it's about to send. It sends the first stop bit. So after that, I turn off the chip select. Then let me go. I send first is 1, then the next one is the start bit. It goes low for the start bit. Then the next one starts sending the bit. You can see it just sent this one here. Then I do it again. It sends this 0 here. Then it sends this 1 here. Then I go again. It sends this 0 here. And I go again. It sends this 1 here. Then I'll go again. It sends this 0 here. Then I go again. It sends this 1. Oh, I didn't reset the data out. Okay, it sends the 1 and then it gives this output here. Let me repeat that one more time. Let me repeat it one more time so you see how it works. I reset, everything is back to, initially it didn't reset because this address latched the output. So let's take it one more time here, but I won't be indicating them again. So turn the address on, turn the CS on, then okay, just watch. Let me take it one more time. Then I reset, turn the address and the chip select on. Then the chip select comes as a pulse. So let me do this. 2, 3, 4. Just watch the TX data bits reacting to this data in. So let me repeat one more time. Let me start with the reset first. Let me reset it back. Address and this here. So then first it sends a 1, it sends a 0, then it starts sending the bits, the 1, 0, 1, 0, 1, 0, 1, 1, parity, stop bit. Can you see it? So this data in from our transmitter has gotten to our receiver, what we received. So that is it about this receiver of the UART. So this is actually the full UART design. The full UART design. Let me try to fix it back. So on the large circuit, you can find the UART somewhere here. This is the UART here, and these connections. Let me just briefly show you around the UART connections. The RS and the TS are connected together. You can see that from here, and they went to the board clock from the system of 5. Okay, I already explained the board clock already. Then the data in, this data in is from the CPU. You have the clear to send, that is from the, it's coming from the device with the RSB. So this is going to the other device we are communicating with using UART, and this coming from us, our transmitter sending to them, and our receiver receiving from them. So that is basically the what we need at the end of the input output of the mini UART. I don't think there's any other thing. So I will still talk about this full circuit and how I did the connections of the whole SoC. in a separate tutorial, but for now we just talked about the mini UART. Thank you.